Hi, Dr. P here, and in this lecture I'm going to be talking about acids and bases. So let's start off with some definitions. Now you probably remember, hopefully, some of the definitions of acids and bases from previous classes that you've taken, Chem 31, Chem 1A, Chem 1B. We have the Arrhenius acids and bases. And so Arrhenius acids will, let's do it this way, Arrhenius acids will increase the concentration of hydronium ions in solution. And Arrhenius bases will increase the concentration of hydroxide ions in solution. The next definition that you've probably seen is the Bronsted-Lowry, sometimes just called Bronsted. And Bronsted-Lowry acids are proton donors. And protons are, of course, hydrogen ions, so I can write that as H+. So proton donors. And then Bronsted-Lowry bases are proton acceptors. The final category, which you may have been introduced to in Chem 1B, is the Lewis definition of acids and bases. So Lewis acids are electron pair acceptors, and Lewis bases are electron pair donors. We also call Lewis acids electrophiles. And we refer to Lewis bases as nucleophiles. So an electron pair acceptor is something that likes electrons, so it's an electrophile. An electron pair donor will donate electrons to another nucleus, hence they are called nucleophiles. Now, we really don't care too much about the Arrhenius definition. It's actually not terribly useful for our purposes. We're going to focus on the Bronsted-Lowry definition and the Lewis definition. And I'll point out that although thermodynamics and kinetics are important for both of these, thermodynamics is more important when we're talking about Bronsted-Lowry acid-base reactions, and kinetics would be more important when we talk about Lewis acid-base reactions. So let's take a look then in a little more detail at these definitions. So first of all, let's look at our Bronsted-Lowry acids and bases. So I could go ahead and write just some general equation here. I could have, let's say, an acid, HA, and of course I'm showing my single bond between the proton and the rest of the acid A. And we will react that with, let's just choose a base B-. And we will get a proton transfer. And so what happens is we get this pair of electrons plucks off that proton. Okay, that can accept the proton. And then we've got this pair of electrons that used to form the HA bond That bond breaks, and that pair of electrons goes on to the rest of what was the acid, A. And so we end up with A minus plus HB or BH. I'll write HB here. And this particular notation is called curved arrow notation, and it's something that you'll see over and over again. A curved arrow indicates something that a pair of electrons is doing. In this case, our lone pair here is forming a new bond with the hydrogen. So the arrow starts at the lone pair and ends at the proton, the hydrogen nucleus. And this other arrow starts at a pair of electrons, the bond, and ends up on the nucleus, A, or the rest of the molecule. We'll talk more about this type of formalism or drawing later on, mostly starting in chapter 6. It's going to become really important for 12A and 12B. This gets into what we call reaction mechanisms. But I just wanted to mention right now sort of what was going on. Now, some other features here. We have our acid, of course, and our base. But on the product side, the thing that came from the acid is our conjugate base. And the thing that came from the base is our conjugate acid. Oops, sorry about that. And we could go ahead and come up with some kind of equilibrium constant for this reaction. We could try to figure out, okay, which side is preferred, and that's something that actually you will want to do, or you will want to learn to do this semester. So let me add paper here and keep on going. So for a given Bronsted-Lowry acid, we can write the following reaction. HA goes to A minus plus H plus. And we have an equilibrium for this this is an equilibrium. We have an equilibrium constant here, which we call Ka, and that's the acid dissociation constant. And you may have seen this in Chem, or you should have seen this in Chem 1B. You may have seen it involving water and the formation of H3O+. But we're just going to focus on it this way. We're going to ignore water, and I'll tell you why in a few minutes. All right, so we have our acid dissociation constant, and of course it is equal to concentration of products over concentration of reactants. So large Ka equals, or means we have a strong acid. All right, let me move this out of the way here, and we'll focus on what's going on here. So we'll have a strong acid if we have a large Ka. Now there's another measure, something called pKa, which is equal to the negative log of Ka. And in this case, a lower, sorry about that, a lower pKa is a strong stronger acid. So larger Ka is a stronger acid, lower pKa, because you're taking the log of a big number, so that's going to be another, reasonably sized number, but you've got a negative in front of it, so that's going to make the number lower. So for example, something with a pKa of 1 is a stronger acid than something with a pKa of 5. Now you guys probably know that. This is a bit of review. I'm not going to talk about Kb and pKb. Okay, I'll tell you how I like to think about bases a little bit later on. So some things to note. We have Appendix B, which is page 425 in the chapter 1 through 12 PDF. And it's a table of pKa values for organic compounds. And I just want to talk a little bit about how you would, let's say, read the pKa table. So I happen to have printed out, I killed a lot of trees and printed out the text here. And I'm going to zoom in here. Let me just see, check my zoom here. And zoom in, zoom in, zoom in. There we go. That's a little bit better. Focus that. That looks good. Okay. So we can see here that something like trifluoroacetic acid has a pKa of 0.5. That means that it's a stronger acid than something like, I don't know, formic acid, which has a pKa of 3.7. And this table is actually several pages long. So we've got, things like acetic acid, 4.8, and let's see, we've got some hydroxyphenols here, 9-ish. What else do we have? Phenol, 9.9. Let's see, what other good things do we have here? Alcohols, so ethanol, 16. We're starting to get outside of the realm we're used to dealing with. We've got an alkyne with a pKa of 25. Acetone has a pKa of 19.3. I always thought it was 20, but your mileage may vary. Ammonia has a pKa of 36. Not ammonium. Ammonium has a pKa of like 9.5 or 9.3. But yeah, 9.3. But ammonia has a pKa of 36. Well, that's just kind of crazy. What I want you to get the sense of from looking at this table is that in Chem 1B, everything you looked at was in water. So when you have H2O as the solvent, that gives rise to what we call the leveling effect. That is, the leveling effect means that the strongest acid you can have in water is H3O plus, and the strongest base you can have in water is OH minus. Okay, this is the leveling effect. If I put a stronger acid, if I put sulfuric acid in water, it dissociates and gives me hydronium ions and then hydrosulfate ions. Okay, it gives me H0 plus and HSO4 minus. If I put hydrochloric acid, I get H0 plus and Cl minus. All the strong acids are stronger than H3O plus. And if you throw those strong acids into water, you get H3O plus and the counter ion, the conjugate base, from that acid. Similarly with bases, if I threw in something like butyllithium, where butane has a pKa of 50 something, 40, probably around 60. So butyllithium then is a really strong base. It'll deprotonate the water, and you'll end up with butane and OH minus. Let me write out some equations just to show that. So Eg HCl plus H2O H3O plus Cl minus. And I drew this as a one arrow, but really it's, it is equilibrium, but equilibrium's way over here. Okay, it's way over on the product side. So this is our strong acid. And let's say I had NH2 minus plus H2O. I used, let's say, sodium amide, for example. And I'll go ahead now and get NH3 plus OH minus. This is my strong acid, this is my strong base. Okay, and again, the equilibrium's way over on this side, and that's because we've got water present. But now, what if we didn't have water present? What if we were doing something in an organic solvent? Well, now we could have other stuff going on. So we could have stronger acids and especially stronger bases than we've seen. So, for example, we could have something like, well, let's look at the following. Let's look at, I'm going to call this predicting acid-base equilibria. And it would help if I showed you that. There we go. Let me zoom out. Sorry about that. I am going to ask your opinion at some point as to which style of videos, lecture videos, you guys prefer. I'm going to record some on my iPad as well. They all have their sort of pros and cons. This is using a new document camera that I got and a different software than Zoom. So anyway, I'll check in with you guys later about that. So for predicting the acid-base equilibria, what we're going to do is compare pKa values of acids. So that means acid and the conjugate acid. And then our equilibrium favors the weaker species. And that would be the higher pKa. Okay, we're not going to worry about Kas because we're not doing ice tables and stuff like that. We're just going to look at pKas. And although you can look at this quantitatively, it's still a little qualitative. Yeah, we're comparing two numbers. But so let's look at an example here. We'll do several examples. So let's say we had CH3COOH plus NH3. Now, first of all, how would I figure out what's going to happen? Well, I can take a look and say that, okay, my pKa here is what, 4.8 or 4.75. pKa of this guy is around 36 for ammonia. And by pKa, that means this guy losing a proton. So this losing, acetic acid losing that one proton, that pKa is 4.75. For ammonia losing a proton, that pKa is 36. So what's going to happen? Well, this proton will go over to ammonia. So I'll get CH3COO minus plus NH4 plus. And now I can look at my pKa. So again, this is my acid, this is my base, and this is my conjugate base, and this is my conjugate acid. And my pKa here is around, I think it was 9.25. I want to say that's right. It's like 9.25. So what does that tell us? Well, I need to compare my acid and my conjugate acid. So if you're given an equation, figure out what your acid is on the reactant side and your conjugate acid on the product side, okay? What has lost a proton? That's your acid. If it loses a proton, it goes from acid to conjugate base. Whatever gains the proton, that was your base and is now the conjugate acid. With the pKa of 9.25, that's higher than 4.75. This is the weaker species. And then my equilibrium is over here, towards the product. Now, you can actually do this mix in water because these are weak, relatively weak acids and bases. This is acetic acid is a weaker acid than hydronium, and ammonia is a weaker acid than ammonium hydroxide. But let's go ahead and take a look at something something a little different. Let's try this. Let's try CH3C bond O CH3 plus NH2 minus CH3C double bond O CH2 minus plus NH3. I should probably start like circling these charges. Well, I'll do that maybe later. Anyway, so what do we have? Well, we have something losing a proton. Our acetone is losing a proton, so that's our acid. And that means we have our base here. And our conjugate base is the acid after it's lost the proton. And then our conjugate acid is what's picked up the proton, when the base has picked up the proton. So my pKa here is, what did I say, 19.2? I think that's right. Let me look in my table here. $19.3. All right. Close enough. We'll change that. 19.3. And my pKa of ammonia is around 36. So, weaker. My equilibrium is way over that way. Now, we couldn't actually do this reaction in water because the amide here would react with the water to make ammonia and hydroxide. And then hydroxide is not a strong enough base to deprotonate. In fact, let me draw that. Okay, so I've got my acid. Let me kind of set this aside here. Let's draw those, make those a little easier to read there. All right, my acid, my base, my conjugate, base, my conjugate acid. So again, my pKa is 19.3 for my pKa is 19.3 for acetone, and my pKa for the conjugate acid, let me look it up here, is, and of course they actually they don't have it listed in the table here. It's actually 14. Older texts will say 15.7, and that's due to the actual expression for Ka and the fact that there's water involved, and water is a solvent. And anyway, don't worry about that. Either one of these is a lower pK or a stronger acid than my 19.3. So this is the weaker species. So in this case, the equilibrium would be on the reactant side. So just notice these examples. One we could actually do in water, but the others involve species that are stronger than hydroxides. Like this base is stronger than hydroxide. This base is stronger than hydroxide. How do I know that? Well, my conjugate acid has a pKa, my conjugate acid of hydroxide has a pKa of 14, so it's a stronger acid than that guy. So my stronger acid came from my weaker base. So that's another thing that I want to, I just want to emphasize is that, you know, we've got our predicting acid-base equilibria. We compare the pKa values, but we can also extend this to predicting just acid and base strength in general. And the way I like to do this is, or the way I like to say it is, we can use pKa values to determine strength of conjugate bases. So what do I mean by that? Well, what this means is that, let me make sure this is still in frame here, there we go. What this means is that the stronger base came from the weaker acid. So let's say we want to figure out some base strength here. So which is the stronger base? This will be an example here. And let's do CH3COO minus or CH3CH2O minus. So we're going to look at conjugate acids. So our conjugate acid for our acetate ion is acetic acid. And our conjugate acid for ethoxide is ethanol. How did I get these? Well, I just added a proton. Okay, to get a conjugate acid, just add a proton. If you have an acid and you want to get the conjugate base, just take a proton away. Now you want to make sure you choose the right proton, and we can talk more about choosing the right proton. My pKa is 4.75 for acetic acid, and it's like around 16 for ethanol. So this guy is the weaker acid. Which means that, well, maybe I'll write it out here, thus CH3CH2O- is the stronger base. Now again, all of this, and I just realized that, there we go, put that back in the frame there. All of this is relative. Okay, the whole point with the Bronsted-Lowry bases let me rewrite that. Hold on here. Bronsted-Lowry acid base strengths are relative. That is, we use them to compare one acid to another acid, or compare one base to another base. And it's important, though, to become familiar with some general trends in pKa's of different organic compounds, so that you know really what to expect. So, you know, we can talk more about the trends. Maybe in class we'll go over more examples. There are some on the practice problems, but just as an example, we can take a look at an alcohol here. R is just some alkyl group. I'm going to call it a carbon chain. Okay, and I could have R. Actually, I don't even need that CH2 there. Sorry, R, and HH, and then R, C, H, H, H. My pKa here is around 16. My pKa for this guy is around 36. My pKa for this guy is somewhere like, you know, I don't know, 55 to 60. These are widely different. We would say that our ethanol is a much stronger acid, 20 orders of magnitude stronger. Okay, that's 10 to the 20th. That's, you know, a hexillion times, 100 hexillion times stronger acid ethanol is than an amine. And then that's, again, many orders of magnitude stronger than an alkane. Now, that's not to say that ethanol is a strong acid in absolute terms. Ethanol is a weak acid compared to acetic acid, and it's a very weak acid compared to hydrochloric acid. So again, I really want to emphasize how these acid and base strengths are relative. Okay, so that's something important to think about. All right, so I think I've gone on for a little while here. My timer says this has been over half an hour, and I think that's long enough. We'll talk more about using pKa values to determine acid-base equilibria and relative acid and base strengths. In the next video, I'm going to talk about some qualitative ways of figuring out acid and base strengths. All right, so until next time, stay safe, Bye now.